and Hai Li from Stuttgart and Duke, respectively, have done a really tremendous job in putting together the contributed program. We have Jianjia Chen as finance chair, Bei Yu from Hong Kong as our publicity chair, and we've also received great support from the steering committee, Paul Franzen, Jörg Henkel, and Marilyn Wolf. Thanks a lot. Without all of you, we couldn't have done it. So much for preliminaries. And now let's get to the main event for today, which is our keynote speech. And for this, I have the real pleasure of introducing Andrew Kahng. He asked me to keep this very short so that he has more time for his talk, and I'll gladly do this. He's coming to us from University of California at San Diego. I think he's very, very well known in our community. So let me just say, he's a fellow of both ACM and IEEE. He has served as general chair of major conferences. And at the moment, he is focusing his attention on a very major project, the Open Road project. And he has been thinking about machine learning for CAD since many years. I think it was 2 or 3 years ago already that he gave tutorials on the topic at conferences. So we're really glad to have you here today with us, Andrew, and the floor is yours.
Thank you, Ulf. Can you hear me?
Yes, I can.
Okay, and you can see the screen.
Yes.
So hello, everyone, and thank you to Ulf and the MLCAD committee for their invitation to give this talk. I hope that everyone is doing well. And let me start with a picture. Scaling drives everything. Scaling is quality, schedule, and cost. There is research and there is practice. And MLCAD is the nexus of learning, optimization, and CAD. And it improves scaling at these red dots. What's not in this talk is open source EDA, which is kind of an elephant in the room in that culture and collaboration and openness at the research to practice interface matter a lot, because this is another picture of scaling. And this is not a good headline. It's from MIT Tech Review last Thursday. And of course, people have probably seen a few of these before. So let me start with the title words, learning, optimization, and scaling. As Professor Christopher Manning posted a couple of months ago, machine learning is the part of AI studying how computer agents can improve their perception, knowledge, thinking, or actions based on experience or data. Optimization is what we do in CAD. I see it as the universal quest to do better. And here's a cartoon of the design optimization problem that tries to make a really important point. Obviously, there's an input, the RTL and constraints, libraries, tech files, and so on, up at the flow start. And then there's many steps and decision points like density screens or useful skew or leakage effort on the way to some complete outcome, routed def and sign-off reports, for example, which is a flow end point, a leaf. And the start to end is very expensive. It takes from weeks to months. We want the best possible end, but there's a huge space of trajectories, and design optimization must stay in a given box of servers, licenses, people, and weeks of schedule. And scaling is what drives all of us in ICCAD or EDA, even when we think that we can drive it. Scaling is the delivery of value. Moore's law is a law of value and cost scaling. And with scaling, what was not feasible before now becomes feasible. We focus today on PPAC scaling. Moore's law is also about time. our world advances at 1% every week. And why we care is that, again, this expands the universe of what's possible. For more than 30 years, manufacturing, the foundry, did the heavy lifting for scaling. So we all rode the wave of Moore's law, putting twice as much onto a wafer every 2 years. And this latest device roadmap shows how Foundry proposes to keep scaling their customers' PPAC value. It's totally heroic, but the complexity of device and process scaling comes with unhealthy economics. And therefore, going forward, we know that more value comes from design technology and from integration technology, like chiplets on interposer or die stacking. Design technology delivers design-based equivalent scaling, which improves products even when nothing changes in the transistor or the manufacturing process. And there's two key directions for this. The first direction advances along a path from DFM to what I call pathfinding. The second direction improves quality, schedule, and cost, which is scaling. And here is where we look to machine learning as a key booster for IC design. And obviously, this is the focus for today. So the two messages just now were, first, scaling is design-based equivalent scaling, and it is achieved by scaling quality, schedule, and cost. And second, optimization delivers quality, but it lives in a box of schedule and cost. There's never enough time or resources. And now the next part of my talk is about learning, optimization, and CAD. And you know, if this were a movie, it would be an epic spanning 60 years already. So picture this. There's three childhood friends. They're best buddies. They're kind of nerdy. They have fun together with A-star search and simulated annealing and SAT. But then they grow apart, and then they meet again, but don't understand each other anymore. Okay, so this is kind of vague. It needs work, but we are living this movie, and we should like to know how it gets to a happy ending. So what can we say about these characters, learning and CAD, or I'll start calling them Ellie and Cade? Well, what machine learning in CAD does spans prediction, will the router finish? Classification, is this floor plan solution viable? Estimating and guiding, for example, what flavor of my leakage recovery script should I run for this particular block? And broadly, MLCAD tries to answer questions that are difficult for human experts, like Google Brain's recent claim of superhuman macro placement. And more immediately, there's a lot of regression and image classification going on, putting jobs onto right-side servers, looking for litho hotspots. We see GNNs, GANs, and many techniques being applied very actively. Why MLCAD? You need models to have predictions. You need predictions that you can leverage in exploration. Crucially, what you can't predict, you guard band, and what you don't explore, you leave on the table. And we really don't like those last two. With the slowdown of process scaling, we are in an era of optimization. We have been for some years, where we now look for ML to win us quality, schedule, and cost. For example, we can use ML to shift the accuracy versus cost trade-off curve in electrical analysis, which reduces the miscorrelation between creation tools and sign-off tools, which improves design schedule and quality. So simply put, we hope that ML will bring us more scaling. This roadmap for MLCAD, which you've seen before, I hope, is becoming quite real. First automate, then optimize using cloud and parallel, build models to predict success versus failure so that design optimization uses its box of resource as well as possible. And ultimately, there's deep RL and superhuman machine intelligence. And I think we're all happy to say that MLCAD is mainstream now, or it's the zeitgeist for some years. We see this in the word clouds of paper titles, session titles and abstracts at this year's DAC and ICCAD conferences, the most popular submission area at ICCAD, and many new technologies inside and around EDA tools with many customer successes for the major EDA vendors. MLCAD is also at the center of where I believe CAD and design automation must go. In the Open Road project that Ulf mentioned, to eventually achieve no human in the loop RTL to GDS, which is clean tape out by construction, MLCAD will need to be everywhere. Decomposition and clustering, parallel and distributed search and optimization, modeling and prediction of optimizers, and other aspects of automation and autonomy. And these mindsets that we hope will get us to predictability and quality and intelligence, these are MLCAD mindsets. And a final point here, if MLCAD achieves ultimate success, it will have transformed itself into MLDA, machine learning enabled design automation. And to me, this is the end goal. So the messages are that the promise of MLCAD is scaling, which is quality, schedule, and cost. And if this community is ultimately successful, it will have created ML-enabled design automation. Now those characters in our movie, CAD and optimization, let me call them CADE and OP. With these two, the phrase, brother from another mother really comes to mind because we know CAD is optimization. It's high-stakes optimizations at enormous scale, where we know how to write down classical formulations and we know the classical optimization or algorithm frameworks, but we need near linear answers and we need the whole thing overnight. And so the reality under the hood of an ICC2 or Innovus is that EDA has always dealt with ever larger problems by applying meta-heuristics and cutting more corners. We've actually been conditioned to not want to beat problems to death because they're NP hard after all. But I want to make the point that this comes at a cost. Never enough time and its consequences have been with us my entire career. A physical design workshop, 1996, the Sun UltraSpark 3 CAD manager was telling us that CAD tools are chaos machines. And when we push hard on a tool that is made up of heuristics stacked on heuristics, the outcome is not just noisy, it's chaotic. You've seen this before, perhaps. The two plots have frequency increasing to the right on the x-axis and area or power on the y-axis. You change the clock period constraint by a sub-picosecond, and you can easily change the netlist area by several percent when the tool is at its limits. And in the left plot, at the highest frequency, the area range is 6%. So how to live with noise and chaos, or embrace and exploit it, is a recurring theme in my group for almost 20 years. And one footnote here is that at SLIP 2020, 11 days ago, we revisited the current state of tool noise, and it's still there. And in macro placement, which is an increasingly dominant step, there is a lot of noise. Because today's users specify artificial blockages at the center to help push macros out to the corners, this GIF shows how much the macro placement solutions can change if a very small blockage is shifted by 6 microns. Interestingly, Tool 1 shows this kind of up to 14% wire length variation, while Tool 2 is more immune to this noise source. So the messages are CAD is optimization, but in practice it's quite heuristic. And piling heuristics upon heuristics means outcomes are noisy and even chaotic. And we may need to rethink what CAD optimization in practice needs to look like in the future. So about the movie, now we have Ellie, Opie, and Cade, 3 nerds and best friends. And there's a kindly grocer who gives them apples and chips every day after school. And that is scaling, by the way. But Ellie leaves town, and Cade doesn't have time for OP, and they grow apart. So, okay, lots of story issues still. But at this point, I hope we're rooting for Cade to be the hero at the end. And so there's optimization and learning, or OP and Ellie. And learning can help optimization in ways that we understand pretty well now. Better prediction of noise or congestion or delay and slew. Always helpful to fit more useful threads into the practical box of optimization resources. I would say that this is definitely the center of gravity for MLCAD thus far, kind of episodic, kind of siloed picking up of perhaps low-hanging fruits. But we're still missing model sharing, standard APIs, big data, and other infrastructure that you'd think of when you hear the word learning. Optimization helps learning with SGD or distributed and federated methods. And there is a virtuous cycle because optimization of hardware also helps learning. And overall, there is this learning optimization virtuous cycle overarching, which helps bring scaling of CAD and design. Let me give just one angle on those scaling opportunities for CAD. Now remember, CAD is conditioned to not want to beat on problems because this costs runtime. But in early design space exploration or the last mile of layout polishing, I feel there's potentially big payoffs if we try harder. Keyword, if we try harder. So for the first one, both ML and optimization can help. And for the second one, I think what I've been calling heavy optimization can add a lot of value. Let me explain about the front-end opportunity, which is in planning and design space exploration. This is from the design chapter in the 2009 ITRS roadmap. What it says is that earlier knobs in the flow grow relatively more powerful over time. That's system level, architecture, RTL. See? But the reality is that we can't get our arms around these early stage knobs for PPA improvement. Design space exploration should ideally explore the more powerful knobs more thoroughly, as shown here. But we tend to budget our attention as shown on the right. And this is because optimizing and exploring in early stages has limited value because we can't predict the back end accurately enough. Our decisions just don't correlate to what can actually be closed and signed off. So we just give up on this and beat on physical design. And the opportunity early is for front-end flow learning and prediction and better optimization, of course. And the opportunity late is for last mile heavy optimizations. Looking ahead, we need a mindset of ML in service of optimization. For example, any learning model should become an objective for some higher level optimizer, even before we get to end-to-end. And optimization in service of ML is just as important. So this is another virtuous cycle. So the message is that there's a virtuous cycle of learning and optimization that brings scaling. And remember, we want good predictors because otherwise we guard band. And we want good optimizers because suboptimality means loss of QOR. And now I'm going to switch gears to a couple of foreground thoughts for MLCAD today. And I'll start with learning. So we all understand that learning means learning from data, and that data in chip design is small and expensive and unique and different. And so there's few-shot learning and off-policy, offline reinforcement learning and so on. And the data is proprietary, so federated learning or layered model architectures, all of which we heard about in Ruchir Puri's opening keynote at ICCAD 2 weeks ago. But let me propose that as a field, we cannot be aiming so low. We know that the right solution, or we know what the right solution is, and we know how semantically trivial all of these proprietary names or formats really are. I'm not talking about the data itself. I'm talking about the missing enablements for data to even exist for purposes of learning. And that means metrics, names, APIs, and concrete existence proofs. So what Ulf referred to, and let's get this metrics slide out of the way. In the late 1990s, there was a metrics initiative for EDA and IC. All design activity would be measured, all data would be mined, and we'd be able to predict tool outcomes, find sweet spots or field of use for tools, and make design-specific tuning of tools. This actually came from Siemens, the semi-custom highway at 1/4 micron, the yellow book. And this is still the goal. And the original metrics system architecture, naming convention, and metrics dictionary are still accessible on the web. Some version of metrics has to become the common infrastructure that unleashes MLCAD. Again, let's not aim low here. The good news is that there is now an SI2 SIG focused on infrastructure to bridge EDA and MLCAD. And some basic questions are, what does a trained model look like? Will we share trained models or forms of models? Can licensed users collaborate toward a model of an EDA tool? What is our open standard way to capture TNS and WNS or DRCs or horizontal overcongestion or VT mix? This is what's called derived data in the language of IBM folks and SI2. And how do we get to big data for model training and validation? And how do we get to trusted models and calibrations? For example, can we use our idle licenses and common or open enablements to develop training data and shared models? And then can we run contests to get better models? The SI2 working group has pointed out that to have data for MLCAD, we need a data model, an implementation, such as open access with extensions, and an API for MLCAD relevant design data and derived data. Most of a concrete solution is already in GitHub. It's the blue box in this picture that the Open Road project has integrated into a single executable, which we call the Open Road app. There's tight integration on OpenDB, which was the foundation of Athena design systems, and on OpenSTA, which is still sold by Parallax and has been in 15 or more EDA tools. So this is an available open source database, extensible data model, and API. It speaks LEF, DEF, Verilog, SDC, SPEF, Liberty, all the standards. We've also been fiddling with Metrics 2.0 for way too long. For anyone interested, there is an available metrics naming convention and a starting set of, quote, mandatory metrics, unquote, coming from advice from a number of EDA customers. And there's a simple JSON format and simple universes of flow stage names, nouns at the run level and the tool metric level, and modifiers like av, max, min, best, worst, est, and so on. So this slide gives two examples of how run metrics or tool metrics would have canonical names. For example, the blue path shows the name for post-CTS, worst setup, timing slack. And this can be tied to corners, runs, designs, and so on. Broad access to real-world machine learning for EDA and IC design will also need to solve the issue of plain old names. Seems trivial, but have to get a solution. We've worked on how to map company-specific names to generic and or, quote, safe names. And this kind of anonymization is also a necessary condition for sharing. And normalization, scaling, noising, etc. may also be needed. So we have a generic name translator that's based on open enablements and open names, such as those in ASAP 7. The translator takes non-generic lib, lef, def, and Verilog and makes it completely generic so that the IP provider, the foundry, or the EDA vendor cannot be determined. And by the way, keep an eye out for ASAP 7, as well as the Skywater enablements that keep on improving in GitHub, or will improve. And last, how do we amass golden data, in particular so that ML can shift that cost accuracy trade-off in analysis? Well, to support academic research, the IEEE CETA Design Automation Technical Committee, DATC, has a new initiative to publish calibration data in a generic JSON form that does not point back to any company or any tool. And this is all part of the IEEE CETA Robust Design Flow initiative, which has been ongoing for more than 5 years. So far, there's PEX and STA, and as of last week, static IR analysis. What this picture shows is that using the RDF 2020 flow, we can generate DRV-free routed designs as the basis of calibration using open enablements. And here you see Skywater 130 and ManGate 45. In the DATC's GitHub repo, you can find .v, routed def, SDC and SPEF, as well as the JSON. For RCX, we publish SPEF files directly. There was some lag there, sorry. For STA calibration, we have JSON for endpoint slacks and full top 5 worst paths. And there's a timing report converter that produces open STA style timing reports from from the JSON, as shown here. And here's the GitHub repo, again, thanks to the IEEE CEDA DATC. And for static IR drop calibration, as I mentioned, this is live as of less than a week ago. The VSRC JSON is an input file with voltage sources information, basically VDD, VSS, and location, to feed static IR drop analysis. And instance voltage JSON is a tool-agnostic report format that captures a list of instances along with their corresponding voltage values. And the last thought on learning in MLCAD, are we totally sure that we know what we want to learn? For example, we might want predictions like 10 milliwatts or 3 gigahertz to be accompanied by recipes or solutions that actually realize those predictions. And given today's chain of heuristic optimizations, I feel we should be careful about our prediction goals. I call this the be careful what you ask for issue. So this was also in that SLIP 2000 paper 11 days ago. Suppose you tell me part of the macroplacer's solution. Shown here for 2 tools on the left in advance, and say you give me exact locations for 9 out of the 28 RAMs in this swerve wrapper core. And I feed them as blue pre-placements to the macroplacer. We see that while wire length might not change a lot, certainly the structure of the solution can change significantly, especially for tool 1 in the top row. And we can ask similar questions about predicting the post-route netlist or the swap cell list after leakage optimization. Does knowing and predicting, say, half or even all of the solution help? For tool 1, the second run will have 10% more wire length than in the first run, not so surprising. And for tool 2, the second run has only 4% more wire length, which is actually kind of great. But it shows that having a precisely predicted result, like the post-route final netlist, makes the wire length worse on both tools. And the point is that even if we have a perfect prediction, we might not know what to do with it. Hence, be careful what you ask for. And the message, we need to unblock the availability and existence of data before there can be learning from data. Let's not aim low. This is not a new suggestion. And we might need to think more about what we want and don't want from our predictions. What are foreground thoughts for optimization? So our CAD heritage is from algorithms, complexity, and operations research. But because we need both capacity and turnaround time, we turn to heuristics. And here's where I have some regret that goes back to DAC 1999 about how we as a field judge new optimization heuristics. The 1990s was when we started to grapple with how to make fair comparisons of heuristics, or even the late 1980s at North Carolina State with Franz Bergles. The meta-heuristics and optimization communities were also asking this same question, and things kind of converged to best solution within CPU budget tau. It's in the blue rectangle. Under this concept, if heuristic A is both faster and better than heuristic B, of course, A dominates B. But here's the catch. If A is faster but B is better, then neither dominates the other, and each has its own merit, especially in the world of optimization. My worry is that as a CAD field, we've lost sight of this. There may be too many paper reviews even today that look like this. The authors achieved 2% better solution quality, but unfortunately, the runtime is 3 times larger. So it is not clear that the proposed method improves over the existing work, etc. This might ring some bells with people. But in deep learning, of course, improving the optimization objective gets credited even if more resources are used. And so I really hope that we haven't shot ourselves in the foot, especially in a cloud SGD, deep networks, 1% is a huge deal world. I think we should be more open-minded to expensive methods that improve quality, CF heavy optimization. And we need better fundamental understanding of how QOR versus resource really works inside our CAD optimizations. So let's think about culture changes, whether in open benchmarking or in peer review. And the last thought is that we really need to think about what noise and chaos and scale imply when we seek predictable, high-quality CAD optimizations. Parallel problem solving from nature, particle swarm optimization. These are very relevant optimization methods as well. And there's a little bit of a when life gives you lemons, make lemonade aspect here. Suppose we go all in on the mantra of only one run needs to succeed, and our EDA is in the cloud anyway. Then we'd use ML to predict distributions and ensembles of outcomes. We'd learn how to manage populations of optimization trajectories. Our flows would intelligently dial up and leverage distributions to keep design in its resource box while getting the best expected outcome. And this is all doable. For example, my students, implemented genetic adaptive multi-start optimization of global routing solutions, which essentially gets to 0 DRCs in the detailed router. And this is with open source academic routers, since commercial tools don't expose the global routing API. From the initial 50 global routes times 5 detailed routes distribution, so that's 250 detailed routing jobs, we can systematically create good global routes by this genetic adaptive multi-start methodology. And by the 11th generation, there's many global route solutions that are robust to detailed router noise and always lead to 0 DRCs. Now, blindly using the same detailed route compute resources, shown in red, doesn't come close to this. Of course, this paper could not be accepted at the conference because it used too much CPU time. So, kind of a fortune cookie message here. MLCAD, which is a nexus of learning, optimization, and CAD, should also rethink some mindsets and culture to make faster progress. And I'll try to wrap things up now. So I started this talk by saying that MLCAD is the nexus of learning, optimization, and CAD, and that it delivers scaling, which is quality, schedule, and cost at these red dots. I know Lots of words to remember here. I feel this is what tomorrow's picture should look like. Schedule is latency. So we have to break through barriers in distributed and federated methods for learning and optimization and CAD. Quality comes from optimization. Maybe with a renewed culture of peer review and benchmarking, we can avoid instances of shooting ourselves in the foot. We can refocus on understanding and scaling of solution quality, as we saw with the machine vision community's example. And with relevant data and metrics, which we have to first enable with infrastructure, we can move the red dots closer to each other, reducing gaps and latencies between research and practice. And about the movie, well, the story has yet to be written. A lot of pieces are missing. There's a long way to go, would be kind of a nice way of putting it. But I think this is where we are today. End of Act 1. So as I said, I'm rooting for Cade, who, to be clear, is us, to be the hero. Every hero has a journey and an arc of change and growth. So how will Cade change? And how will the movie end? So I hope this community will write a great story together. And I hope everyone has a great workshop this week. Thank you very much for your attention. How did I do? 40 minutes. Too short. I'm sorry, Ulf.
It's just perfect. Thank you very much,
Okay.
Andrew. And by the way, we have close to 90 people attending out of about 125 which have registered for the workshop. Thanks again for this wonderful talk. And the floor is open for questions. As I said before, if you have a question, either just unmute yourself and speak up or type it into the Zoom chat or the Slack chat. Maybe I'll kick off with one question, which you touched a bit on. So you talked a few times about the chaos that results when you stack one heuristic on top of another heuristic. And yes, I certainly agree to that. What I'm wondering is, so there's heuristics, which we use in traditional CAD, but there are also well-developed deterministic optimization algorithms for certain tasks, where in certain cases we can even prove that they're optimal. How do you see the relationship between such optimal algorithms, which admittedly, of course, always solve some sub-problem? So the relationship between such deterministic algorithms and machine learning.
I think machine learning can help us learn objectives that are still optimizable. I think one important issue is, well, there's many important issues around your question, but when it comes to optimal methods, generally they run out of steam at a certain instance size. It's one problem. And our instances are huge. So we need decomposition, stitching, clustering, problem size reduction, many ancillary techniques to attempt to apply optimal methods in the first place. Second, the optimal methods often need a convenient objective. And I think this has been a big problem that, you know, there's nice spectral or analytic placement methods, but ultimately there's an art to getting these to fit the actual EDA challenge or design need. And so learning can perhaps help us understand how to search the hyperparameter space for the deployment of our optimal algorithms. Learning can help us with clustering or some sort of more automated, less human involvement, use of distributed and cloud resources that are running our deployed optimal algorithms. And learning can also help us, find these optimizable objectives that more accurately reflect what we really want to happen. And that's that part of that stack of models becoming objectives as you go up the stack of the flow and try to work backwards. Does this answer your question?
Yeah, it gives me definitely a perspective. Yeah, thanks.
That's not a yes.
And I think this is a discussion which also will continue over time as machine learning becomes more powerful. And yeah.
Yeah, there's no questions in Slack.
Yeah.
Okay.
So I have a question.
Please go ahead.
Yeah. So you know that the machine learning methods such as neural networks, they produce the results that is a probability. So we cannot guarantee the 100%. So I'm wondering whether the neural network aided optimization for IC, should we combine the neural network aided optimization with the current optimization methods to achieve the final optimization without human intervention?
I think that's the end goal. I think, for example, Google's very famous archive paper does apply deep reinforcement learning to the macro placement problem, and then the rest of the way, a commercial tool, they press the button. So this kind of hybridization of, I think, early in the flow macro placement, hybridized with a standard follow-on in the commercial flow world, or conversely, using neural networks as people have done with, let's say, detailed routing or congestion prediction or DRC prediction and other sort of evaluators of layout, that can be an adjunct to the traditional flow as well. Essentially, you'd have a constant time evaluator that replaces an expensive heuristic optimization. So I think hybridization of neural networks or other AI ML methods with traditional tools and flow is very doable. Is this what you meant?
Yeah, yes.
Oh, okay.
Thank you.
And who were you? I'm sorry, I can't see on my screen.
My name is Grace Lee Zhang. I'm from the chair of Electronic Design Automation, Technical University of Munich, under the supervision of Professor Schlichtmann.
Thank you.
Thank you.
So we have one question in the chat from Peter Domansky. Is machine learning even capable of predicting chaotic behavior?
Predicting chaotic behavior. I feel that sampling techniques can help us learn with as few samples as possible, maybe even in an adaptive learning sense, or active learning sense, and there's also sparse sampling techniques. To better understand the distributions that result when we twiddle various hyperparameters or knobs in our heuristics. So actually, I'm missing this. Oof. It's in the chat. Okay.
Yeah, it's in the Zoom chat.
Oh, shoot. Okay. Is ML even capable of predicting chaotic behavior? I think it can help us learn distributions for sure. And I kind of blur chaos and noise. You know, chaos implies that if you change just a very slight aspect of the input, the output changes by a lot. And noise is simply you get a distribution of outcomes. I kind of blur the concepts in what I say. But I would say that sampling and learning distributions is probably what I'd mention in response to Pete's question.
Rajiv, can you try again?
Yes. Hi, Andrew. Can you hear me?
Yeah.
Yes.
All right. Good morning, good evening, everybody. And Andrew, thanks for a brilliant talk as always. I want to pick up on what I thought was a central keyword in your whole talk, that is heuristics. And, you know, many of us, especially me, who started in CAD 40 years ago, recall how we tried to find these very beautiful analytic closed form expressions to solve optimization problems. And, you know, Ulf will relate to this because I had discussions in the good old days with Professor Antreich about this, who was extremely good at closed form expressions. And then we all slowly drifted into heuristics as we realized that we really couldn't solve these, you know, closed form formulation problems because of NP completeness, or, you know, simply couldn't solve the equations, the techniques didn't exist. And we got so used to the heuristics that we forgot that it's all heuristics based. And I really appreciate that you highlighted that in your talk and reminded us that that is the core of our problem where we are today. So here's my question to you. Yeah. We resorted to heuristics because we had nothing else. Now that we have data-driven techniques with machine learning, do you think there is a hope that machine learning-based algorithms could actually replace the heuristics and start giving us more deterministic solutions where the designer has a far better control than just shooting in the dark and turning knobs here and there to try to get the tool to do what he's doing? So any comments on that?
I think so. I mean, I sometimes have a slide about the bitter lesson of Rich Sutton, which is that eventually deep learning and feeding this gigantic deep network every single result that has ever occurred in the history of mankind, yes, or every single cat face, you know, it eventually swamps out everything. And so, you know, sometimes if I'm feeling dark, I put in this picture of the fulcrum, and, you know, who's going to move the fulcrum so that, you know, that puts off the day when deep learning just wins, which is the bitter lesson. So yes, I feel that machine learning definitely, you know, has the promise to win and to solve our optimization problems. And yeah, I think I'm glad that you picked up that point about shooting ourselves in the foot. We really have to emulate, I feel, what goes on in the ML and machine vision communities. We have to focus on quality. And it's been a pity that we've ignored good methods that achieve solution quality improvements at the cost of let's say, CPU time on a single thread. Because now we have many threads and we have distributions that we can sample from. So we should be happy that those better methods are available.
Thank you.
Okay. Did I answer your question?
Yes, very well. Thank you.
Okay, thanks. And then I see that Mark Wren has a question. Can you elaborate more about the notion that detail optimization stage might benefit a lot from ML? I think that's kind of similar to Rajiv's question, which is that we've already seen that for certain very small, let's say, gate sizing or critical path optimization, same thing, or even detailed routes. For example, going back to DAC 15 and trying to predict good clock buffer surgery based on some sort of machine learning approach, I think detailed optimizations will benefit kind of from the bottom up, and they'll start with sizing and detailed routing or DRC fix kinds of things, and they'll work backwards up the stack is my hope. Mark, I don't know if that's what you were expecting, or?
Yeah. So I was thinking about we talk about global optimization and the detail optimization, right? So usually the global optimization, you want to achieve sort of some theoretical guarantee that you are within some close range of optimal within your approximation bound, right? So but for detail optimization, usually it's already within that bound. You just try to improve a little bit. So that's why I want to know what you mean, if why do you think there's all a larger improvements that we can make on the detail optimization? But it seems like you're talking about basically if machine learning can solve the detail optimization problem, then probably we can move up to solve the global optimization problem.
Right. And my point is that right now, high dimensional dynamic programming or min cost flows with larger instances, we just don't even try them in commercial tools because they're too expensive. I mean, we could do a lot better perhaps in CTS or other important stages if we spent more time. So I'm hoping that whatever can be sort of stubbed out as an ML model, will help us explore more of the solution space, and that's likely going to happen bottom up in terms of how we think of the flow. And I see that there's a Asma question in chat about ML models where everyone collaborates on. If I may answer it,
sure.
Certainly it's the same company / tool, but I really believe across the industry, and that's why I think the notion of privacy preserving or IP preserving data transforms is going to be very key. I mentioned primitive ideas that undergraduates can implement, which is make library cell names so that you can't tell whether they came from TSMC or ARM or ST or some other source. And of course, this is not proven to be privacy preserving, but I believe the technology exists for this. And I think the notion of who owns data, is it Qualcomm and Broadcom or NVIDIA on the customer side, or is it Synopsys or Cadence on the tool side, where the tool has produced, in some sense, the solution from which the data is derived? This is an important question to resolve. This is where I might have mentioned, well, there's always open source, and there's always trying to learn the model of the closed source solution from open source solutions. As open source tools get perhaps better, that modeling task will be easier. And so there's many ways that water can flow downhill here. I just think that we should go beyond what Ruchir mentioned in his keynote, which was, multi-layer modeling stacks or architectures and few-shot learning. I think we should aim for what we really need. And that's to Asma's question.
Yeah, Andrew, thanks a lot. I'm afraid we're pushing up, or we already have pushed up against our time limit. So let me thank you once again for this wonderful opening keynote. I think that's a great way to kickstart this workshop. Thanks again. As I said earlier, we have the Slack chat available. So if you have further questions, I'm pretty sure Andrew will be happy to answer them in the Slack. And in case he is still around when we start the virtual social event, maybe you can catch him there. Thanks again, Andrew. And with this, I hand over to Hussam, who is going to moderate the first contributed session.